Humanity has really embraced the radio spectrum. When you think about your daily life, you have a radio device in your pocket, multiple radio devices on your body. You are transmitting to and from radio towers all around your city. You have Wi-Fi in your home, and then a bunch of other kinds of radio that's used by air traffic control and other radar systems. Like, radio is everywhere. It's not going anywhere. Radio is getting even more ubiquitous over time. And there was a really interesting paper that I saw a couple of weeks ago written by Dr. Michael Garrett. And it was about how alien civilizations could map planet Earth just by watching how our cell phone towers rise in the morning as different continents become operational in the morning, between the day and the night side. And you could actually not only start to map out the continents of Earth, but you could start to even get a sense of the cultures of Earth when you think about various times, the ubiquity of our radio transmissions around planet Earth. So I had a very fascinating conversation with Dr. Michael Garrett. He is the Sir Bernard Lovell Chair of Astrophysics and the director of the Jodrell Bank Center for Astrophysics, and focuses on astrophysics, but as you will discover in this conversation, definitely a huge fan of SETI, searching for any kind of evidence of extraterrestrial civilizations. We talk about how humanity's just transmission in the radio spectrum has expanded over the decades, and what we will be capable of looking for when the next generation telescopes come online, like the Square Kilometer Array or the next generation Very Large Array. We will suddenly be able to see out to 100+ light years of range and detect planets like Earth boiling in radio transmissions across all of these spectrums. So, fascinating conversation. Here it is. Enjoy. So, from the perspective of an extra solar civilization, what would Earth look like in the radio spectrum?
Well, I think it would look very noisy and very bright. So we already know that because, I think 30 years ago, we had the Galileo probe. Before it went to Jupiter, it kind of swung by the Earth. And they made those measurements of, the radio emission that was coming from the Earth. And I think Carl Sagan was the person that really convinced NASA that that was a good idea. And I think it was a really good idea. I don't know why they hadn't planned it right from the start. But there you see that the thing that's really unusual about our planet is really the fact that it has all this sort of narrow band, so these very narrow frequency radio signals coming from it. And I think, as Sagan concluded in that paper, that's the obvious thing that tells you that there's something weird going on this planet, and that weirdness is, the fact that we have a technological civilization.
That idea of using a spacecraft as it's doing one of its gravitational assist flybys of the Earth to examine the Earth from the perspective of an exoplanet and say, if we could see this from space, would we know there's life here? And that, you're right. Yeah, Carl Sagan sort of defined that idea, but it's been done many times now with different spacecraft as they all do their flybys. It's like one of the, test your camera and also figure out if there's life on Earth. And some spacecraft are able to, and some aren't.
Yeah. Now, I think the thing about the spacecraft that were going to Jupiter and Saturn, like the Pioneer, Voyager, Galileo, they have radio instruments on board, and if you're going to Mars, you probably don't have a radio instrument on board. But if you're going to the outer planets, because they're also producing lots of natural radio emission, then they already have those instruments on board, although they're typically at lower frequencies than the frequencies that maybe we're most used to when we talk about, when we look for signals out there. So they're typically much lower frequencies than, we think about when we're doing our own searches. But yes, and of course, it's not the only indicator that there's something a bit weird going on here. You have the fact that you detect oxygen when you look at the atmosphere, not at radio wavelengths, but further up in the infrared and the optical, you see, and oxygen. Well, oxygen just reacts, all the time. So if it's in the atmosphere and you detect it in the atmosphere, that usually means, well, something must be generating that oxygen continuously, because otherwise it just reacts with other compounds on the planet. But if you see it there, then that tells you, yeah, something's producing oxygen. And the thing that does that for us here on this planet is photosynthesis, mostly from plants, but also in the ocean, for example. So that's another indicator. The fact that we have water in the atmosphere, we have CO2. Also, you could see all the sort of pollutants that we produce, like nitrous oxide, et cetera, So, all in all, across the electromagnetic spectrum, there's a lot of indicators that this planet is a little bit different from maybe your typical planet, although we don't really know what a typical planet looks like. But, there's all the indicators, I think, that something strange going on here, even just in the optical and the sort of, not the spectral line, but in the continuum. The fact that we have lights and those lights shine into space, although that would be very difficult to detect. But if you were passing by in a spacecraft, you can certainly see that. And that also tells you, that there's something very interesting going on this planet. And hopefully that's also the same on other planets. But, you might have to search through many planets before you find that.
Yeah, I mean, one glance at Earth at night, and you would see all of the city lights and you would go, there's life there. I know that in the past, the scientists were thinking about those things that you mentioned, oxygen present in the atmosphere of a planet, maybe ozone, maybe methane, various kinds of chemicals that are produced by natural sources, but then don't last very long in the atmosphere. And so there has to be something that is replenishing them. But as more and more eyes are on this work, it really seems like there are natural sources of almost every one of these potential biosignatures that have been found so far. And that the emphasis is starting to shift over to some of the ideas of the technosignatures, because for the longest time, searching for signals from aliens was considered ridiculous. And now there's actually a sizable amount of people that are doing this kind of work, and it feels like searching for technosignatures is going to get the job done that you have. So, why does a technosignature give you a more certain answer than perhaps some kind of biosignature?
No, I think you kind of summed it up really well, that we don't know very much about planets in a sense, but we do know that there are many different ways to produce, some of the molecules that you talked about, like oxygen or methane, and they may not be biological in origin. They might just be outgassing, from deep within inside a planet, for example, and you might just be lucky to see oxygen, that day or that year. We even know from Mars, for example, like the levels of methane, they change very, very quickly from one day to the other, or from one part of the planet to the other. Whether that's biological or not, or whether it's just some intrinsic property of the fact that the planet deep down contains those kind of molecules and releases them due to certain conditions like spring coming or summer or whatever. So I think it's really complicated, and I think it'll remain complicated for a long time, and I think there will be multiple interpretations for those biosignatures for a long time as well. The thing about the technosignatures and the really definitive thing about technosignatures is that you really need a technology behind them to produce them. Nature just doesn't produce narrowband radio signals. It just doesn't happen. And we've been looking at the radio sky for 100 years or almost 100 years. And we know really what radio stuff does, what planets do in the radio, what stars do in the radio, what galaxies do in the radio. And although they produce spectral lines, yeah, but they never produce anything like the kind of artificial signals that we produce, that, Carl Sagan detected with Galileo when it came back, these really narrow band, very, putting a lot of power into just a few channels, few frequency channels. Nature's not going to do that. I mean, why would it do that? There's really no reason. There's no mechanism for it to do that. The only way you can do that is with technology. So I think it's a game changer in the sense that, if you detect something like that, there's really, you would think of, well, what could be the natural explanation for this? But I think you'd be hard pushed to come up with something that was kind of reasonable, that wasn't a bit convoluted and a bit complicated. And the obvious thing is that, this is technology that produces this. And you're also right that, there's a real rejuvenation in the technosignature research that's happening across the world. And for example, projects like Breakthrough Listen, I think, have absolutely transformed what's happening, not just in the US, but actually coming out and getting all the interest. There's a huge amount of interest throughout the world, all over the world, in this area, and just nurturing that. And you see that, the people that are doing SETI or technosignature sort of surveys today, first of all, there's a lot more people doing that. They're much more distributed across the planet. And often they're coming from sort of traditional astronomy survey backgrounds. So it's quite a different place now than it was maybe even 10 years ago, and certainly 20 years ago. So there's a much different perspective on how we should be doing these surveys. And also there are more resources through, projects like Breakthrough Listen, and there's access to, the best telescopes on the planet. And in addition to that, getting the right people who are interested in this topic, who would never have been employed in this topic before, but, not just the astronomers, but also people with really good technical backgrounds and good computing and software and analysis and AI, just bringing that all together, bringing them with these really, top-notch telescopes, having a real professional attitude to the way it should be done, just like a normal astronomical survey attitude. Bringing all those together means, I feel that we're really only just started on the SETI journey in the last few years, to be honest.
Yeah, it feels very different, though, than what it did in the past. Like, when I used to interview astronomers who were interested in this kind of thing, we'd have to talk about their main research, and then in hushed tones, we would talk about searching for aliens because they were fans of that idea, and maybe there's a couple of papers every now and then, but now it really does feel like a renaissance. So how do Earthlings, how are we the brightest? What do you think is the most obvious technosignature that humanity is sending out into space right now?
So I think probably it's, we're obviously producing a lot of radio waves, right? But the most powerful radio waves we send out are also kind of the rarest. So, we're sending bright signals out to maybe Voyager, through the DSN, the Deep Space Network. And maybe that happens, I don't know, a couple of times a day, or, it doesn't happen all the time, right? So you have to be, if you're an extraterrestrial, you have to be really lucky to sort of intercept that signal as it comes through. So those bright, powerful signals like the DSN, but also radar signals, they're quite sort of pointed on the sky. They're not there all the time. They're at certain frequencies. Those happen quite rarely, but they're probably the sort of big obvious thing. If you've got a telescope that can see all of the sky, for example, and is on all of the time, then maybe those would be the easiest things to detect, just because they're the brightest things, they're the things that go boom, but you might have to wait a long time before you detect them from our planet, but also any other planets that are out there. Field of view, the amount of sky you can see would be really important in this. And then you have then you have the stuff that we've been talking about recently, which is the fact that, we've all got these, these mobile phones, everyone's got it on their back pocket, or, you've got my laptop, for example, your laptop using Wi-Fi. You've got a little box in your house that's producing a lot of radio waves. You've got all the mobile towers that are connecting all these devices together. So we have these sort of very not so bright sources, fainter sources, but they're everywhere. No matter where you go, you're totally surrounded by all these radio waves being produced by these low-level devices. So you have this background coming from the Earth that we didn't have, 20 years ago. We had it a little bit, but that's just increasing enormously from the fact that there are billions of these things.
Right.
Billions of them.
For the podcast listeners, he's holding up a smartphone, but yeah.
Yeah, sorry. Yeah. So there's absolutely billions of those. There's millions of mobile towers that connect all the smartphones together. And then, how many Wi-Fi systems are? I don't even know a number for that, but basically most houses on the planet probably have one. So we're talking about billions of devices again, and they're all producing this sort of low-level emission. But I think that's really interesting because we didn't have that, 30 years ago, we just did not have that. So that's something that has really just appeared. There's no sign that this is something that's kind of going to stabilize. It seems like we have a real thirst for bandwidth, video, so you need to have, occupy lots of frequencies to convey that information. So I think this is kind of the new kid on the block in terms of technosignatures at this very low level, but it's there and it's spreading its wings, if you like. It used to be a sort of narrow frequency range, but you go from 3G to 4G systems to 5G mobile systems, and the main thing that happens there is they're just using more and more frequency space. So this is a really interesting development. I think it's really interesting because, would we have predicted that 30 years ago? Maybe some people would have, but most people, felt that radio was on the decline. I listen to people a lot that say, oh yeah, well, we don't use radio any longer. And I'm thinking, well, we don't use radio? I mean, we're totally immersed in radio waves everywhere we go. Whether we're inside our houses or we're outside our houses, we're totally immersed in radio waves. And yes, we don't use it so much in the radio. We don't use it so much for TV because there are cable systems. But, this whole mobile communication system, Wi-Fi systems, totally dominated by radio. So we're becoming much, much brighter in the radio, I would argue, than fainter, as some people have argued, I think, incorrectly. So let's in the recent past.
Yeah, so let's talk about your research then. So you worked out like a map of what the Earth would look like as the Earth is turning, seen from an alien perspective. What would they see?
Well, I was inspired by this old paper from 1978 by Sullivan et al. It was published in Science. It's if you haven't seen it, it's a great paper. That paper also tried to think, well, what would aliens see if they were observing us at this point in time, 1978 or whatever. And, they concluded the brightest sources would have been, the bright TV transmitters and the bright radio transmitters at the time. This was well before, cable TV or satellite TV. Those were the ways that you sort of listen to the radio or you watch the TV. And radar systems. The radar systems are still with us for obvious reasons, and I think that the TV and radio are also there, but they've changed somewhat. Like we have a lot of digital systems and things like that rather than the analog systems. But they're actually also there as well. But the thing that I was really interested in was, this was a great paper. It showed you the fact that, the radio emission would vary as a function of time for any alien just because the Earth rotates. And so, sometimes you see areas of the Earth where there were more TV transmitters, and sometimes you saw places where there were less TV transmitters. So there was a sort of modulation in the signal that an alien would detect, if it had a single dish radio telescope pointed towards the Earth. And, they worked out also that you could probably discern certain things from those signals. The fact that some areas of the Earth seem to use, one frequency, and then other areas of the Earth used another frequency. They might have got the idea that, there was different standards, and that maybe different countries or different regions and things like that.
Oh, it's really interesting. That you could learn a bit about the culture just by sensing the radio transmissions.
I don't think we've really done a good job also now on exactly everything that you could discern from this. I mean, when I see what astronomers do when they look at data, and they look at data really carefully, and the nuances they can pick out of the data, I think you could do a really good job. If you did, especially if you have very fine time resolution, that you can see that signal, how it changes. You could discern things like. Not just the fact that maybe there were different countries and different standards, but also that most of us want to live on the coast of these big continents. Where most of the cities are actually, the big cities are really not in the middle of the land regions, but actually on the outskirts, where I guess where we started, where we were fishing or whatever. I don't know exactly, but yeah, I'm sure. And obviously, you just pick up the fact that the Earth rotation is goes round on its axis once every 24 hours or 20 whatever. So you could discern quite a lot from that, and we were inspired to try and redo this beautiful paper from 1978, by Walt Sullivan and published in Science. We were really kind of inspired to think about, well, what's different, now compared to then, and the obvious thing to me was not that radio had got fainter, but actually that radio had got brighter. And it got brighter with this very kind of weird, in a sense, very distributed sort of system of mobile towers, but also, individual mobile devices. And they sort of culturally, that's quite interesting as well, because the distribution of those is quite different from the way things were in the mid-1970s, where there was the domination by North America and by Western Europe. The TV and radio transmitters, they basically dominated the predicted signal. And now you see a kind of much more even distribution, obviously not in the ocean. So if you're an alien and the Pacific crosses in front of you, then it's very quiet still. But you only have to wait a few hours, and then all the major land masses come into view, and then your signal picks up again. But that signal is really quite different from the TV and radio signals that we had then, in the sense that a lot of the developing countries, certainly Asia, of course, but Africa, for example, where mobile communications are really so important for the economy, for the culture, for the communication, they are probably even more important than it is for other parts of the world. That you see that there's emission coming from these places where, in the past, at least in the TV and the radio, these were quite quiet areas, but nowadays these are actually quite bright areas of emission.
And when we think about these radio signals traveling outward in space like a sphere, and this every year that goes by, they've moved one more light year out. And this is a trope that's been used in science fiction to have the aliens discover us and then come to visit or return the Voyager spacecraft to us or what have you. But like, if you took Jodrell bank and flew it out into space and then looked back towards the solar system, how at what point would you no longer be able to detect the emissions coming from planet Earth? Like, what do you think the range is with our current, and maybe the fast telescope? Like, I think about like the current capability of radio telescopes on Earth to detect and start building this kind of a map. How far can we see?
So I think, if you took the fast radio telescope, for example, those radar systems are going to be still bright. I would imagine, 100 light years, you're still able to detect our radar systems reasonably easily. The mobile stuff that I've been talking about, that's much fainter. So you'd only be able to detect that, I think, within a light year or a few light years, for example. That would be more difficult.
But what about say when the square kilometer array comes online?
So the SKA, I mean, that would be very capable in many different ways. So that should be able to detect those radar systems. Also at 100 light years, a few hundred light years. But differences with the SKA is that you'll be able to sort of pinpoint the location. With fast, you could detect the signal, but you wouldn't really know where it's coming from. You just know that it's somewhere within that beam that it puts on the sky. But with the SKA and later, with NGVLA, for example, hopefully that also gets built, then you'll be able to really absolutely pinpoint the location. You'll be able to pinpoint the location so that, it wouldn't just be, if it was coming from a star or a planet going round a star, you'd see radio emission coming from something that was offset from a star in your field of view. And if you waited, depending on the distances, you'd see it moving as well with the SKA. So localization is really, really important. And single dishes, even fast, just doesn't do that for you. If you start using multiple telescopes, then you're going to be able to do really interesting things that will, you might have an interesting signal from a single dish. It might look artificial, but you don't really know where it's coming from. So to be absolutely definitively sure that it is what you think it is, i.e., another technological civilization out there, I think localization, pinpointing the location of that signal and also, watching that signal move, possibly coming and going, if it's on a planet, or if it's on a spacecraft, see it move at, it doesn't have to move, at a large fraction of the speed of light, but if it's moving like Voyager or something like that, then you could discern that, certainly with, very long baseline interferometry where you have telescopes, across the planet. To me, that's the thing that we should be kind of preparing for, that we need to start thinking about how we're going to do that, because, we are kind of, in this period of making these big surveys with, the Green Bank telescope, with the Parkes telescope. We're sort of maybe on, that boundary of going from non-detection to detection. So we need to start thinking about all the things that we're going to want to do when that detection happens and prepare for it.
Yeah, I mean, when you think about how many star systems there are within 1 light year of us, and the answer is none. But when you think about how many stars there are within 100 light years of us, now we're in the tens of thousands, possibly 100,000 stars within 100 light years of Earth. And so the number of targets that we can study goes up exponentially. And I'm sure tests and other telescopes have found some interesting candidates that we would love to be able to do some follow-up observations with these. And for those of you who missed it, you mentioned, there's the square kilometer array, the SKA, and then this one in North America, the next generation very large array. When you think about when you think about Contact and Jodie Foster sitting in front of all of those amazing dishes, but spread out across North America with a vastly wider series. And this is, so we're going to have not just the one, but the 2 super radio telescopes and
also covering, a very wide frequency range. So the SK sort of covering the more traditional range, maybe up to 20 gigahertz, but NGVLA going from 20 gigahertz up to 100 gigahertz. I think we one of the things that we see today on this planet is that move towards broader band mobile communication systems, which means you have to go to higher frequencies to get that bandwidth. So we need to be able to do this technosignature search, not just at low frequencies, but also at the higher frequencies. And obviously you want to do it across the electromagnetic spectrum. But, I think we also need to be thinking of higher frequencies in the NGVLA. We need to be thinking about ALMA, because although, we don't do much communication at those really high frequencies on the planet because we have a lot of water vapor, so it doesn't really work very well. But when you're in space, when you're above the atmosphere, communicating at those really high frequencies, like point to point, within a solar system, I don't mean like across the galaxy, but, between one star and another star or within a solar system, those high frequencies become interesting because they have all the nice properties of radio waves, but they also, you can convey a lot of information on them, because they're so high frequency. They've got a lot of bandwidth.
Like X-rays? There. Like if you is that how high a band?
I'm not thinking of X-rays, but who knows? I mean, I wouldn't rule anything out, to be honest. But I'm just thinking of we're kind of focused at the moment on sort of this gigahertz regime. That's where our microwaves work. That's where our telephones work, etc. But why not go 3 orders of magnitude higher up to the terahertz range? That's like the body scanners at airports, a little bit further down than that. But those also have the capacity to convey information. We just don't use them here because they don't go very far, because they get impeded by all the water molecules that we have in the atmosphere. But if you go into space, for example, I wouldn't be surprised if there's a lot of space communications, in the next few decades that are using those kind of frequencies to convey information, because then you're, above the atmosphere and you're just point to point in space in a vacuum. So we go to much higher frequencies at some point pretty soon, I think.
We're seeing the rise of these satellite mega constellations like Starlink and the upcoming Kuiper, and I'm sure the Chinese are building their version of this. How do you think that will change? Because now suddenly you no longer have your continents. You now just have this buzzing cloud of satellites.
Yeah, I think it's incredibly exciting. It's in some senses really bad for radio astronomy.
Yeah. For your needs at Jodrell Bank, it is not good. But
no, it's not good. But it's also exciting in a sense because you're seeing the technological evolution of a planet kind of in front of your eyes. In a lifetime, you've gone from, TV and radio is it, and radar. And then, you think, mobile communications, that's also a big thing now, like 30 years later. And then maybe, 10, 20 years later after that, we're thinking about these constellations. So everything's evolving, everything's changing. But radio is still radio is the big common denominator between, from Marconi all the way to Musk, M to M, if you like. The radio waves are still the basis of that communication. And I find it, kind of challenging because, radio astronomy is going to find it difficult to operate with all those satellites, beaming down around 10 gigahertz, also that shift to the higher frequencies that we talked about earlier. And, what does it mean? What will that look like to an outside, another technical civilization looking at our planet? What's that going to look like? Well, those satellites are all pointed down towards the Earth. But there will all obviously be kind of leakage, beyond the Earth at certain points. Plus, there will be, I'm sure, there will be uplinks to those satellites happening, to command them and et cetera, et cetera. There may be intercommunication links between those satellites, I would imagine, also for new applications, I think. I mean, my feeling is, we want to model this. I'm not sure exactly how to model it at the moment.
It sounds like your next paper in the works.
Yeah, I think it will be our next paper at some point. But I think the bottom line is you can't have all that activity. You can't have 100,000 Starlink satellites in orbit by the end of the decade. Plus, as you mentioned, I think there are like 2 or 3 Chinese systems as well that are being talked about on the same scale. There's OneWeb as well as Starlink. I'm sure Europe is probably thinking about this as well. So how many satellites are we going to have in low Earth orbit before the end of the decade? It's definitely many, several hundreds of thousands of satellites. It could be even 1 million satellites in low Earth orbit before the end of the decade.
If they organize their constellations in a way that fits with shells and stick to your lane, there could be tens of millions. Like there's room. Space is big. There's room. As long as you don't go helter-skelter about it, then there could be a lot of satellites up there.
Yeah. So that's going to be incredibly interesting because they're all using radio waves to do whatever it is they're doing. And a lot of those radio waves won't reach their destination, just like radar systems, they send out, a lot of radio waves, but only a tiny fraction ever comes back. And, I think obviously we need to do the modeling of these systems to see how they work. But to me, it means that from an alien perspective, there's going to be this kind of very red hot sort of potato out there in space. That is our planet, and I think it certainly makes us more detectable than we've ever been before.
Yeah, well,
that's for sure.
And like intrinsically brighter. Like before, we had very individual, very powerful radio transmitters or television transmitters.
Yeah,
but this makes us bright just as an entire planet.
Yeah, it makes us bright, but it also just across all frequencies as well. So, we'll be, it's not like radar that maybe is only working, at a few megahertz at, 1200 megahertz, with a few megahertz bandwidth. This whole, the constellations and the Wi-Fi and the mobile devices and going from 4G to 5G to 6G to 7G, however that goes, they're just consuming spectrum, so they're going to higher frequencies. And, it's an absolute measure of the technological development of this planet,
People always make this argument that the reason we don't see alien civilizations is because they go to wires, they go to fiber optics, they go dark from an external perspective. That sounds impossible to me, with everything shifting to satellites. And then as we extrapolate to a solar system spanning civilization, what are you going to do? Run fiber optic cables from here to Jupiter?
Yeah, I think you're right. It's really difficult. And the fact is that humans definitely want mobile communication systems in their back pocket. So I don't think you're going to be happy with a fiber, trailing a fiber around. You want, it's a mobile system because, it's mobile. You want to bring it wherever you want to go. And you don't want it wires and wireless in the sense, that old fashioned term, really beats wires every time. You want to be wireless. You also, if you want to charge your telephone, you don't want wires. If you want to communicate, you don't want wires because it gives you the freedom to do whatever you want to do, but be connected. So, I'm sure fibers have their place. There's no doubt about that. But when you're outside and you're moving around, the fact that radio waves can, they are able to typically, traverse lots of different media like windows or even thin walls, not thick walls typically, but thin walls that they can bend round corners from one room to the next. You have, one Wi-Fi system typically does a modern house, and also in your garden and all that. Radio just has that advantage of being really good at going around corners and keeping you connected. It's difficult to see how, fibers or wires would ever be able to do that. I just don't see that. That's possible.
So then let's sort of project forward and think about the future. Like we're going to have this gigantic constellation of satellites shortly. We will be setting up some sort of research station on the moon. We'll set up research station on Mars, on nearby asteroids. Fast forward 100 years from now, 200 years from now, and we will potentially have humanity across the solar system interacting, communicating. Based on sort of your understanding of what works best in space, what does that look like? If Earth becomes this very hot, mini bandwidth object that's bright in the radio spectrum, an entire solar system spanning civilization, what would that look like?
Yeah, I think, if you look 100 years from now, as you say, I mean, hopefully if things keep on going reasonably well.
Yeah, if the robots let us do this.
If AI or whatever lets us, get there, or we don't fight each other too often or whatever. The possibilities are just amazing, I think. And, as you say, going to the moon, going to Mars, occupying, a significant fraction of the solar system, being present there, maybe mining asteroids or whatever we want to do. We're going to have to be able to communicate to be able to do those things. So I'm not sure that radio will be the way that we do that, because I think as we go into space, that a lot of the stuff that we'll do is kind of point to point, planet to planet, or spacecraft to spacecraft, so above the atmospheres of these planets. So I think, for example, laser communications are going to, at some point there will be sort of exponential growth in that area, I would imagine. Radio will always be there just because of the fact it does stuff that higher frequencies are not able to do. But I think we will see, that continuous shift towards higher frequencies and going not just into, the millimeter range, but into the infrared, even into the optical, but definitely into the infrared. We're going to become brighter at all frequencies. It's hard to extrapolate beyond maybe a few decades, to be honest. Probably stupid to even try.
Yeah, but I don't mind getting a little stupid, but I guess, when you think about this shift, like I think 20 years ago, the idea was, let's look for a directed transmission, some alien civilization that is sending us a message. And now it really feels like the emphasis is starting to move towards, let's search for leaked transmissions not intended for us. Do you think that's feasible or the better path forward at this point?
I mean, to be honest, I think we need to try everything, right? Because, we haven't detected anything, so we absolutely have no idea where it's coming from, what it will be, whether it'll be radio or whatever. So I'm absolutely kind of agnostic about, we should be doing, this, that, or the next thing. I feel that we need to be open-minded, that we need to try and do everything that we can do with the technology that we have. I don't think there's a silly sort of technosignature SETI idea. I don't think that exists. Maybe if you detect a signal, such a thing exists, but until then, everybody has a good idea on this. I think leakage radiation, does have the advantage that we know that we do this. We don't send beacons really very often out into space, and if we do, then we do it for, very short periods of time, a few minutes, and maybe a few minutes every decade or so. The cadence is really, really small. So, looking for leakage radiation, I think that's something we should be thinking about, because, every technological civilization is going to have such a thing, certainly when they're at our stage of development. Maybe later on they can cloak themselves in some way if they want to do that, but at least we know that we're pretty open about being here in a sense. But it would be difficult for us to stop it. We don't have the technology to do that. So I think leakage radiation is really interesting. And also, I think it sits maybe a little better in comparison to biosignatures as well, in the sense that, biosignatures is also not something that's kind of predetermined, or you require someone to do something. It's just a natural implication of having life on a planet, in the same way a technosignature is a sort of natural application of having an intelligent technical life form on a planet. So you would imagine that there's much more chance of detecting those leakage signals. Oxygen is also a kind of leakage signal in a sense. So it's none of these things are incredibly bright, so they're difficult to detect. But there might be a lot of them out there to detect.
A lot of people who are sort of young in their career, thinking of choosing science as a career, interested in astronomy, and fascinated by the search for aliens. I think it is one of the most important questions we can possibly ask in science is are we alone in the universe? What's the best way for a person who is excited about these ideas and is maybe an undergraduate in university now and wants to make a career of being an alien hunter? What's a good way to go about it?
Well, I mean, I think, get a good physics degree or a good astrophysics degree, first of all. Probably you need to go and think about doing a PhD. I don't think you need to go directly into sort of SETI or technosignatures when you do your PhD. I think you can do it after you've done your PhD. I think that's almost healthy in a sense, because PhD gives you, you're specializing typically on something, but you're also learning at a higher level more about astronomy and astrophysics, and our careers tend to sort of converge more and more onto sort of particular things that we're interested in. So I always think it's good to start as broad as you can. You have your undergraduate degree, you have your graduate studies, and you begin to focus more and more. But after your PhD, or even at your PhD stage, being interested and wanting to do technosignatures, there's nothing embarrassing about that.
Yeah, not anymore. It's perfectly legitimate.
I mean, this is a big question, and people, normal people are interested in it. They want to know the answer. They expect people that know how to do this kind of stuff to do it. It's a good use of public funding, just because people want to know the answer. They're interested in it. It's just like, right up there in terms of what the public wants. And the public pays for what we do. And we cannot have some kind of high ground where we think, oh yeah, variable star studies are much more interesting than working out whether we're alone in the universe. I'm sure variable star studies are really interesting, but I think we do have to realize, who pays, our wages at the end of the week. And we have to do what we're interested in, not just what we think we're interested in, but actually the stuff that motivated us. When we were 10 years old, or whatever, for me, apart from Star Trek motivating me, and Star Trek was very much about going out there, trying to find out, is there life out there? What kind of life is out there? Those are the things that still motivate me now, almost 50 years sort of further on. And I know that other young people are like that as well. And there's a lot of other stuff that you're going to discover, on the sidelines of that pursuit. I think it's really important that people that do this have a broad understanding of astronomy, to be able to, understand what's artificial and what's natural. We have to combine that. But we just have to get away from this idea that this kind of science is somehow not quite as good as, other kinds of more traditional sciences. Because, eventually we're going to, I think, I hope, we're going to detect something. It's a bit like gravitational waves. It took decades for people to detect gravitational waves. It took interferometry to come along before we could detect gravitational waves. And people worked on it for many, many years. And I think SETI's at the same point at the moment. The fact that we have dedicated people, we have dedicated resources, we have great telescopes, we've got fantastic back-end digital systems, we've got great software, computing, we've got AI, all these things are coming together. Exponentially, our capacity and capability increases year on year on year. You know, if there is a detection out there to be made, we're getting closer to it exponentially. And once we make that detection, the world will be a different place.
Yeah, it's back to that Arthur C. Clarke quote that either we're alone in the universe or we aren't. And either possibility is terrifying and exciting. So, well, Michael, absolute pleasure to talk to you. Good luck with your hunt for signals. And if you do find aliens, would you let us know?
Oh, absolutely. Yeah.
Sounds good.
I'll give you a call.
All right. Perfect. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at university.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Just Paul Davis, Vlad Shipolin, Jay Dennis, David Giltonen, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Andrew Gross, and Josh Schultz who support us at the Master of the Universe level. All your support means the universe to us.